Thanks everybody for being here. My name is Stefan from Hoff. I work at the Royal Netherlands Space Center, NLR in short. I'll be talking today about simulation models, particularly on models used for certification as opposed to training. Content of the presentation. First, I will introduce the RoCS project in a little bit more detail than I just did. Then I'll talk about certification by simulation as more as a concept. We'll move into talking about simulation model fidelity. Finally, some remarks. So the RoCS project, as stated by Andrea already, it's part of the Clean Sky 2 research program. A question. The partners in the RoCS project, we have two universities, Liverpool and Cranfield. We have, three universities, Bolivia as well. Two research institutes, NLR and DLR, and one SME from Italy. Leonardo is a topic manager, and EASA, I'm not sure it's formally a partner, but at least it's part of the project. So, this was something that I did change. I'll just skip this slide like this. So the main goal of the project is really to look at standardizing the use of simulation in certification. So the ultimate output of the project should be a set of guidelines that can be used by any applicant, that is supported by the authority, and that will help make applicants use simulation more often in their certification process. So the RoCS project obviously has a number of work packages. Right now I want to focus mostly on the first two, but work package number one focused on identifying from the certification standards which elements of those we think are or potentially could benefit from certification by simulation. There are certain aspects where we think the ability of simulation models just isn't there in the near future to replicate flight tests, but other parts where we think in the near term this could potentially be either augmenting flight tests or replacing flight tests. In the second work package, we look at the simulation models and what fidelity they would need specifically for the certification paragraphs we identified in the first work package. Then there's a third work package that is focused on the queuing. So what does the simulator need to look like? There will be a separate presentation on that later today. And finally, as stated, the output should be a set of guidelines. So we have to gather all the findings from the preceding three work packages, put out some form of guidance that hopefully is accepted by the community. So certification by simulation obviously has a lot of potential. First off, it's basically the triangle you saw in the previous presentation. First one is risk. Obviously, flight testing inherently is risky. Some flight tests more so than others. And mitigation of those risks is not always possible. And flight simulation provides a means of testing the extremes of the envelope in a safe manner. Second one is cost. Flight testing obviously is expensive, and particularly if it involves relocating a team and an aircraft to some far-off place in the world, or when you are relying on environmental conditions that may or may not be there. Flight simulation, on the other hand, is right as your design office. Go in any time of day. So obviously that's a cost-effective alternative, only dependent on the fact on whether or not you can reach the level of fidelity and validation in a cost-affordable way. Finally, effectiveness. Simulation allows you to explore a great number of configurations and scenarios, more so than with flight tests. And in some cases, flight testing simply isn't possible. As mentioned previously, eVTOL is a good example of that. Fly-by-wire failures is another example. So in some cases, flight testing simply isn't an option. In those cases, typically simulation is already accepted. Obviously, there are still challenges that we're facing. Otherwise, simulation would already spread use. First and foremost challenge is fidelity, not only in achieving the required level of fidelity, but also in defining and measuring the level of fidelity that's needed for a specific certification task, and doing so at an acceptable cost. Another challenge, which is different from the use of simulation training, is validation. Obviously, every simulation needs to be validated, but in this case, at least a portion of the flight test data simply isn't there. So you will have to rely on some measure of extrapolation. And that could be in altitude, it could be in the proportion of the maneuver, but somehow we need to demonstrate that the simulation is credible, also outside of what we tested. So in terms of current practice, we saw already in the previous presentation that simulation is being applied already in certification. The certification standards allow for this to some extent. Specifically in paragraph 21, it states that compliance demonstration must be shown by tests upon an aircraft of the type for which certification is requested, or by calculations based on an equal in accuracy to the results of testing. So simulation is in this case a form of calculation, and equal in accuracy, I think, is an interesting statement that we'll come back on later. If we look at the guidance for certification standard 25, it's a fixed wing standard. They already mentioned 3 of these, so I'll skip those. I think another example for where certification or simulation is already allowed, accepted, it's in supplemental and derivative type certification. So it's a little bit of a different scenario because it presumes that you have demonstrated your compliance on the aircraft by flight test previously, and now you add a modification in the flight test. So it's a slightly different scenario, but the other ones obviously by demonstration too risky, environmental conditions are difficult to attain, we have multiple pilots and you need to show repeatability, and failure cases. Looking at AC25 again, fixed wing guidance, it talks about the criteria that apply to the simulation we're trying to use for certification. It says a number of things, but amongst which are that the simulation should be of a type and fidelity that is appropriate for the task. So that's very vague. I'm not sure what anybody can use from that. It also says that the level of substantiation of the simulated flight correlation should be commensurate to the level of compliance. Very nice sentence. Basically means that the closer you are to non-compliance, the more accurate your simulation is. And obviously the simulation should be suitably validated by flight test for the conditions of interest, but that does not mean that the flight test should be at the exact conditions of interest. So this allows for a measure of extrapolation. Stated this is fixed wing guidance. If we look at Rotorcraft guidance, we do see already acceptance of extrapolation, but it's not necessarily by simulation. But it talks about altitude extrapolation, for instance, and it's different for different parts. So, for instance, for hover, takeoff, and landing performance, altitude extrapolation. But there are other parts of the extrapolations that are, well, we have shown that there can be rapid changes depending on altitude for the extrapolation extent. Whether or not these limits can be extended if we base the extrapolation on simulation.
Kannst du hier zwei zusammenschmeißen? 35, hast du geguckt bei
Genau,
später?
damals haben wir bei geguckt und
Mute your speaker.
I think it's Marcus, which has the microphone open.
da hat auch Stefan hatte
Warte mal.
gemacht.
Can you mute them?
Ja.
And in the meantime, I'll organize it here.
Ja.
Right, so another example of current practice is eVTOL, but there's such a presentation that I won't go into any detail. Example was already presented in the previous presentation by Andrea, power off landing, 189, but also other aircraft. I just wanted to highlight here that the guidance specifically for this maneuver, because it's been recognized a long time ago that it's a difficult and dangerous maneuver to perform. So the guidance specifically for this maneuver already states that simulation can be an acceptable alternative. That is not the case for many of the other certification paragraphs. So future perspective, what it is we're working towards is a standardized authority accepted use of flight simulation to support, augment, or replace flight testing for Rotorcraft certification. And talking about flight certification status. That also means that there will likely need to be a shift from certification flight testing to flight testing specifically. So development flight testing, so flight testing for certification will be expanded with dedicated testing towards validation with the aim ultimately of producing demonstration compliance flight tests, total the number of flight tests. Talking about simulation fidelity, I don't want to go into a lot of detail on everything. So just a few items to highlight as a sort of a starting point. We are presuming that depending on paragraph and the certification standards, we'll either use a desktop or a pilot simulation. Pilot simulation might be hardware in the loop if so needed. But simulation in that sense is not restricted to pilot simulation. We are supposing that the simulation needs to be physics-based because we are relying on this model to explore parts of the envelope that haven't been tested. This is quite different from the approach taken for training simulators where there can be physical tuning as long as the pilot feels no difference, then it's okay. But for certification type approach, we would have a model that predicts the actual physics. And doing so with minimal empirical tuning, because as soon as you tune a specific condition, who's to say that that tuning also applies? And there needs to be validation by flight test, not in the exact conditions that we're certifying for, but at least there needs to be some proof that the model is performing accurately. There are other bullets in here in the latest version. I think one of which is that there needs to be a controlled development process, just like there is in any other part of the certification. demonstrate that simulation model you're running is traceable and specific configuration you are certified. When we talk about simulation fidelity, we're actually talking about two different things. One is the predicted fidelity and the other is the perceived fidelity. One is just, does the model recreate reality? And the second one is, does the pilot feel that reality? Together that forms simulation fidelity. In this presentation, because I'm talking about simulation model fidelity, I'm not really talking about aspect. So one of the questions is, what requirements do we need to set for fidelity? Can we specify a particular requirement for all of the standard? Probably not. So how do we go about defining how good the model needs to be? The typical approach that's being used now for training simulators is tolerances, typically plus or minus 10% on a number of parameters. And this works well for training. It's been demonstrated to work. It's been used for a long time. It's intuitive. People really understand what it is you're talking about. But one of the questions is these tolerances, this plus or minus 10%, where does it come from? And is it suitable for this particular application? It seems to work for training, but what tolerances do we actually need for when we apply it to certification? Another drawback, if you purely follow the CS FSTD standards, is that there's no dependence on the proximity to non-compliance. So that's not in line with guidance from AC25. So the closer you get to non-compliance, the more accurate model, therefore tighter tolerances. And we know from past experience that it's possible to develop a model that meets the requirements for the CFSTD, but the pilots will not rate them with the same handling quality. So if you're using simulation for a handling qualities assessment, obviously you're going to have the same handling quality. So tolerances by themselves do not appear to be sufficient. Talking about handling qualities, you very quickly start talking about ADS 33. There's some advantages there because obviously it's a handling qualities rating allows you to measure not only task performance but also the compensation of the pilot. It involves both time and frequency domain metrics. We know that purely a time domain lose some information. But again, here on the con side, tolerances need to be justified. You have these nice charts, boundaries for different handling quality levels. But just on the boundary, does that imply a different tolerance? We don't have an answer to that at the moment. The question is also whether those tolerances should be dependent on the level of compression of the pilot or on the underlying handling qualities. And the handling qualities themselves don't have a direct relation to the compliance limits. So again, using just the ADS 33 type metric alone won't get you what you need. Another approach would be to look at maximum allowable error. And this is just an example of, in this case, y-axis being collective, x-axis being bird weight. So you can imagine the simulation can be used to predict what your control margin is over the full range of your envelope, but you might not have flight test data. So for the part that you do have data, you can demonstrate what your error is relative to flight test. But then how does that error develop over time? But still your simulation does predict a certain margin, margin from the limit. So in essence, your allowable prediction error should be equal to that margin. Because if you predict you're there, then you're safe. Obviously, that's not in line with the equal and accuracy statement from Stichting standards. So the question is whether or not this is allowable, is acceptable. Probably not if your prediction error becomes very large. So some of the questions to be answered when we talk about fidelity beyond the tested envelope. So one is, can or should we define limits for the allowable extrapolation, not just altitude, but any other extrapolation dimension? Second is, what is an acceptable time domain error tolerance in the validated part of the envelope, given the allowable error at the extrapolated conditions? And if you're going for that type of approach, what's the minimum number of validation data points that you need in order to gain confidence that you can accept extrapolation? These are open questions at the moment. I don't have definitive answers to any of them. But there are possible ways forward. One would be to demonstrate the evolution of the predictive error across whatever simulation dimension we're talking about for a given environment using historical data from the past. So we're doing this now within RoCS using the AW18109 as the basis, but that's just one aircraft and one simulation environment. So in order for us, community, to make statements about how the predictive error evolves, for instance, over altitude, you need to have more information, more historical data, other aircraft, other types of simulations. Another way to look at it would be to try to quantify the uncertainty in your simulation using, for instance, uncertainty quantification techniques, where you try to predict what the probability distribution is for whatever output you're looking at. So then, can't really see it here, but you'll get a large number of simulations, some of which will predict that you are exceeding your certification limit, and there will be probability associated with those, and you need to find a certain minimum probability which you can set. Sounds very nice. In practice, it's difficult because it requires you to define probabilities for all the parameters in the models. So how uncertain is your CLCD? It's not an easy question to answer, and therefore also the approach is not easy. But it is a way to gain more confidence that your simulation is giving us the right result. Haven't tested it. Haven't flight tested it. So concluding remarks, flight simulation promises certification, time, cost, and safety benefits, but an authority accepted guidance material is needed in order to allow its routine application to no longer is the case. Challenges still remain in defining, measuring, and in achieving at an acceptable cost the level of fidelity that's required for the specific certification task. And data from previous test-based certifications from various OEMs would be needed, or at least desired, to demonstrate that the predictive error beyond the tested envelope is behaving in some sort of predictable way. That was the last slide.
Okay, thank you very much, Stefan.